Hi, good morning. Am I audible?
Yes, sir.
Audible, right? Okay, so today we will start. We'll continue organometallic chemistry. Up to what we have done?
Isolable analogy.
Isolable analogy we have done. Okay, so yeah, let me share the screen. Yeah, screen is visible, right?
Yes, sir.
Okay, fine. So today we will start uh, metal carbonyl complexes. Okay, metal carbonyl complexes. So this metal carbonyl complexes, these are basically are of two types. Okay, two types. One is actually your homoleptic. Okay, and another one will be your heteroleptic. Homoleptic and heteroleptic. So homoleptic means what? Homoleptic means only carbonyl ligands are there. Okay, carbonyl ligands are there. So suppose you have this chromium, then you have what? CO whole 6. Okay, only carbonyl ligand is there, so that is your homoleptic compound. Suppose you have this Ni, then you have what? CO whole 4. Okay, so this is actually your what? Homoleptic compound. Now apart from carbonyl, if you have an other ligand, so suppose you have this compound chromium CO whole 4, then you have PPH3. So this is basically your heteroleptic compound, or I can write down also like this, that chromium CO whole 3 NO whole 2. So this is what? This is also your heteroleptic compound. So if you have only carbonyl ligand, that time it will be homoleptic. Apart from carbonyl, if you have any other ligand, suppose PPH3 or NO nitrosyl ligand, that time it will be your heteroleptic ligand. Okay, heteroleptic ligand. Okay, just a minute. Fine. So suppose I have this compound vanadium CO whole 6. Can you tell me how many electrons are present here? How many electrons are present here in vanadium CO whole 6?
Total valence electron.
Uh,
17.
17, right? So here you are getting 17 electron. Okay. If I am getting this chromium CO whole 6, here how many electrons are present?
18.
18. Similarly, suppose you have this manganese CO whole 5. Here
17.
17 electron. Okay. If you have this copper CO whole 4, so here how many electrons is present in?
15 electrons.
How 15? Copper is what? 3D10 4s1, so 11 electrons from
4
your
to 8.
copper and 8
19
from
electrons.
so 19 electron is present here. So if you see the atomic number for vanadium, the atomic number is 23. Okay, for chromium it is your 24,
24.
manganese is your 25,
25.
and copper is what? 29.
29.
Right. So you can conclude here that if atomic number, okay, if atomic number is equal to odd, you are getting odd atomic number, so that time what it will be? So write down that 18 electron rule 18 electron rule does not satisfy does not satisfy in neutral condition. Okay, so if the atomic number is becoming odd, that time the 18 electron rule will not be satisfied in neutral condition. Okay, fine. So suppose here you can see chromium. For chromium the atomic number is even 24, that's why you are getting 18. But if your atomic number is odd, that time 18 electron rule will not be satisfied. So what we have to do, so here we are getting two methods by which we can satisfy the 18 electron rule. So write down that two methods two methods two methods to satisfy two methods to satisfy 18 electron rule. Okay, two methods to satisfy 18 electron rule. Number one is what? Number one is your dimerization. Okay, dimerization. So dimerization will take place if your coordination number is less than 6. Okay, this is one dimerization. And number two, another thing you can do, so that is your bi electron capture. Okay, so that compound, if it is dimerized, okay, so that time it will satisfy 18 electron rule. And another option is what? It can abstract one electron. Okay, so these are the two possibilities we have. So and for dimerization, what is the condition? That coordination number should be less than 6. Okay, if it is greater than 6, then it will be problematic. Okay, so coordination number should be less than 6. So suppose I am giving you one example. Suppose CO whole 4. So how many electrons we have? So for cobalt I will get 3d7 4s2, 9 electrons from cobalt center and 8 electrons from this carbonyl. So I am getting 17 electrons from this species. And cobalt is what? Cobalt is 27. So atomic number is odd, that's why it is not able to satisfy 18 electron rule. So what will happen? Now this compound will dimerize. So if this compound dimerizes, what you will get? Cobalt bond cobalt, and this side you have 4CO carbonyl. Okay, this side you have 4CO carbonyl, this side also you have 4CO, this side also you have 4CO. Okay, now you can calculate that cobalt you are getting this COCO4 actually 17 electron, and if you consider this cobalt bond, so you can get one electron. This cobalt center will get one electron from this bond, and this cobalt center will also get one electron from this bond. So basically you are getting 18 electron. Okay, or you can calculate for the whole compound, you will get 36 electron. Clear? Clear? So that is what? That is your dimerization is happening here. Okay, here what is happening? Dimerization is happening.
So what is the meaning of dimerization?
Dimerization means this is your one COCO4 unit and this is your another COCO4 unit. Now they two are adding with each other. Okay, so if you take 2 mole of this compound, 2 equivalent of this compound, they are adding with each other. That is your dimer.
Okay, sir.
Dimerization means this is actually, suppose this is your monomer and this is another monomer. If you add 2 monomer, you will get a dimer like this. This is your dimer, and singly they are monomer. Okay.
Okay, sir.
So if you take 2 equivalent of this, you will get this dimerization. Okay, and you can see what is the coordination number here. What is the coordination number? How many bond it is forming? So 1, 2,
5.
3, 4, 5. So coordination number is 5. So that means it is acceptable. Coordination number, if it is less than 6, that time dimerization will be possible. Okay, dimerization is possible. No problem is there. Okay. Clear?
Yes, sir. Clear, sir.
Okay. Now second we have by electron capture. So in electron capture, suppose you have this same example I am taking CO whole 4, and with this CO4 I am adding one sodium metal. Okay, so generally sodium is what? Sodium is a metal, and what is the tendency of sodium? Sodium releases one electron to become sodium plus. Okay, so it releases one electron to become sodium plus. Okay, and whatever the electron it is releasing, that electron is accepted by which? This compound. Okay, so sodium is becoming sodium plus, and this CO whole 4, that is actually accepting the releasing electron from the sodium, so it will become CO4 minus. So you can now check how many electron system. Cobalt is 9, from carbonyl you will get 8, and for negative charge you will get 1 electron. So ultimately you are getting 18 electron. Okay, so these are the two process. One is your dimerization, and if you react the same compound with a metal, suppose sodium, lithium, potassium, alkali metals, so that time they have a tendency to release electrons, and if the metal center is releasing electrons, the compound will take up the electron, and it will also get up what? It will also get 18 electron. Okay, so these are the two methods we have. Now suppose you have this vanadium CO whole 6. So how many electron system it is?
17 electrons.
17 electron. So what can happen here? Dimerization or what?
So with electron capture.
Why?
Because of less than 18.
No, less than 18. Both system are less than 18. Na? Here also it is less than 18. Here also it is less than 18.
So coordination number will be 7.
Coordination number will be 7, correct. So if you do here dimerization, so here you have vanadium bond, okay, and this carbonyl. So basically you have 6 carbonyl, CO, 3, 4, 5, 6. Here also you have CO, 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 CO. So if you can see here, the coordination number is actually becoming 7. Okay, and when it is becoming 7, so what will happen? The steric hindrance is increasing. Okay, the steric hindrance is increasing. That's why it is not favorable. Okay, if you are getting higher coordination number than 6, that means the steric hindrance within the molecule is actually increasing when you are doing dimerization. So this dimerization will not take place. Okay, basically it has initially 17 electron, it wants to get 18 electron, but dimerization is not the process. So what is the process? What can happen to get 18 electron? Electron capture. So you have to provide some metal center, sodium amalgam, like that. If you provide this, sodium will release the electron, and vanadium will become vanadium CO whole 6 minus. So now you will get 18 electron here.
And last one CO4. How you are getting 18 electrons per cobalt?
So cobalt is 9 electron, from 4 carbonyl you are getting how many electrons? 8 electron.
8 electrons.
And this one bond is actually forming by how many electrons? 2 electrons, na? So if you have 2 electrons, so that means what? This is covalent bond, na? Covalent bond. So covalent bond means what? This cobalt center is donating, sharing 1 electron, this cobalt is sharing 1 electron. So 9, 8, 17, and this 1 electron 18. Okay. And for this cobalt center 9, 8, 17, and this 1 electron 18. If you calculate for the whole compound, you will get 36 electron. Clear?
Yes, sir, clear.
Fine. So these are the things. Okay. So basically we have two methods to satisfy the 18 electron rule. Fine. Now next we will do, write down that molecular orbital molecular orbital diagram of CO. Molecular orbital diagram of CO. Okay. So initially, if you see carbon double bond O, okay, carbon has 4 electrons, carbon has 4 valence electrons, 2 electrons is forming here, so that means 2 electrons left. Oxygen has 6 valence electrons, 2 electrons is forming here, and 4 electrons is there. Okay, now if this oxygen donates 1 electron, if oxygen donates this lone pair to here, so what will happen? We can write down carbon triple bond oxygen. So this oxygen is becoming positive charge and carbon is becoming what? Negative charge. Okay, this oxygen is becoming positive charge and carbon is becoming negative charge. Okay, so this is basically the resonating structure. Now we are asking about the molecular orbital diagram, so we have to do the MOT. So initially, suppose carbon is what? Okay, I am drawing from here. What is the electron configuration for carbon? 1s2 what? 2s2 2p2. Right, oxygen will be what? 1s2. I am writing only the valence electron. Okay, so 2s2 2p4. Right, so first of all I have to take the 2s orbital. So take the 2s orbital. Okay, now which one is actually more electronegative? The energy will decrease for that. Okay, so I am first of all I am drawing the energy axis here. So this is your energy axis. Energy is increasing from this bottom to up. Okay, energy is increasing from down to up. Okay, so suppose I have here carbon. Okay, this is 2s orbital and this is for your carbon atom. Okay, similarly this side you have, this is also 2s orbital, but this is for your oxygen atom. Okay, so here you have 2 electrons, here also you have 2 electrons. Okay, so what I will get, this is what? This is your sigma 2s and this is what? This is your sigma star 2s. Okay, so 2 electrons, so what? Overall you have 4 electrons, so fill 2 electrons here and 2 electrons here. This is your bonding orbital. This sigma 2s is what? This is your bonding orbital. And sigma star 2s is what? Anti-bonding orbital. That you know. So very good. So this is your 2s. 2s is done for us. Now next is your 2p orbital. So write down here 2p orbital. So you have 3p orbital. This is for carbon. Okay, this is for your carbon, and here you have 3p orbitals, which is for your oxygen. Okay, oxygen. So yeah, so basically if you see here, so carbon has 2 electrons, in p orbital you have 2 electrons, and here in p orbitals you will get 1 2 3 4. Okay, so if you mix them up, what you will get? You will get these orbitals. So this is what? This is your sigma 2pz. Okay, this is what? This is your pi 2px. This is what? This is your pi 2py. This one is what? This is your pi star 2px. This is what? This is your pi star 2py, and this is what? This is your sigma star 2pz. So 2 electrons from here, 4 electrons from here. Overall you have 6 electrons. So 1 2 3 4 5 6. Okay, oh sorry, I done one mistake. Sorry. Yeah, here actually Here it will be like this. Basically pi 2px and pi 2py will be downside, sigma 2pz will be high. Sorry. So 1 2 3 4 5 6, if your sum of atomic number, okay, sum of atomic number, if it is your greater equal 15, then only the sigma will come down, otherwise not. Okay, so if you see here, carbon is 6 and oxygen is 8, 6 plus 8 is 14, so that means no need to change anything. But if it is greater equal 15, suppose for NO it will reverse, but for CO it will not. Yeah, so that is the thing. So yeah, now the question is here that, okay, this is the whole molecular orbital diagram you have. Now which one is your HOMO and which one is your LUMO? So if you see this sigma 2pz, okay, this sigma 2pz, this is basically your HOMO, okay, highest occupied molecular orbital, and these are the lowest unoccupied molecular orbital, this pi star and pi star 2px and 2py. So this will be your LUMO. Okay, so this one is your HOMO and this one will be your LUMO. Okay, clear?
Yes, sir, clear.
Now if you see this sigma bond, okay, this sigma bond, this sigma orbital, that will be more close to this your carbon atom, okay, because we are doing this carbon and oxygen, okay. So basically this sigma, okay, this homo actually, this is actually closer to your carbon orbital. So you can write down here this HOMO, okay, I am talking about this sigma orbital only. So you can write down here that slight, okay, slight of antibonding character, slight of antibonding character. Why? Because it is actually moving in the upper side. See, this is your antibonding orbital and sigma 2pz is actually closer to that, so you will get slight antibonding character also, okay, and it will be closer from your carbon atom, okay. So you can write down here also that you will get here maximum carbon character, okay, you will get here maximum carbon character, maximum carbon character. So yeah, this is the thing, okay. You have to know this CO MOT, because basically in interview they can ask you that, okay, CO is donating electrons, because we will do back bonding and those things. Now basically what they ask, okay, CO is donating electrons, so from which orbital it is donating electrons. So that time students was unaware like what to say, because usually they will say like this, sir, carbon oxygen, so carbon is donating these two electrons, but they want to know specifically the orbital. So that time you have to mention that, sir, it is donating from this sigma 2pz orbital, because this is the HOMO. If HOMO is there, okay, higher the HOMO, that is the donor ability will also increase, okay. So this CO ligand, okay, CO ligand is donating the electrons from the sigma 2pz orbital, and if metal is back donating electrons to your CO ligand, that time it will accept in these orbitals pi star 2px and pi star 2py, because these are the LUMO orbitals you have, okay. So we have HOMO orbital, we have LUMO orbital, this thing. Suppose you have metal and this is your CO, so CO can donate electrons to the metal center. If CO is donating electrons to the metal center, so that is actually donating from your sigma 2pz orbital, okay, sigma 2pz orbital. And when metal back donates the electrons to your CO orbital, so that time it will occupied by your which orbital, that time it will occupy the electrons in your pi star 2px and pi star 2py orbital. Clear?
Yes, sir.
This concept should be clear, because they asking several times, explain the bonding of CO. Fine. So if it is clear, now we are moving to this. So now write down this thing, that bond order, okay, bond order, this is actually proportional to bond strength, bond order, this is actually proportional to bond strength and which is inversely proportional to your bond length. Okay, so that means if your bond order is increasing, bond strength will also increase and bond length will decrease. How to find out bond order? I think that you know, right? What is the formula to find out the bond order? Half of what? Number of bonding electrons minus number of antibonding electrons. Okay, number of bonding electrons minus number of antibonding electrons. So if you see here, how many bonding electrons you have? How many bonding electrons you have? Here you have 2 electrons, which is basically bonding. Okay, here you have 2 from here, 2 from here. This is actually your bonding and that is also bonding, right? Sigma 2pz. So overall I have 2 4 6 8 8 bonding electrons. And check how many anti-bonding.
2 electrons.
Anti-bonding, yeah, here you have 2 anti-bonding electrons, so do it. 8 minus 2, so 6 by 2, so that means specifically what?
3.
Okay. Okay, fine. So this is the thing. Okay, okay, fine. So now let's show how the bonding is happening. So suppose you have this carbon, triple bond O. Okay, this oxygen is positively charged, carbon is negatively charged, and here you have 2 electrons. Okay, now it is donating the electrons. This CO is donating the electrons to the metal center. Okay, CO ligand is donating the electrons to the metal center. So this is what? So first of all, write down here that every ligand is sigma donor at first. Okay, so if it is donating only these electrons, only one lone pair, so that is basically a sigma donor. So every ligand is sigma donor at first. So where it is donating? The CO is donating to the metal orbital, right? CO is donating to the metal orbitals, right? So from which orbital it is donating? So that will be this sigma 2pz. Okay, sigma 2pz. Now the second step will be that, so one bond will form here. Okay, one bond will form here like this, because carbon is donating electrons to the metal center, so one bond is forming. Now metal has d orbital, that you know. Metal has d orbital, so it has also electrons here. Metal will have electrons in its d orbital. So what will happen? Metal will back donate the electrons to the back end orbital of your CO. Metal will back donate the electrons to your back end orbital of CO. So here write down, I am talking about only the CO. Okay, so here the HOMO will be what? Sigma 2pz, and this is actually what? This is actually known as your back bonding. Okay, this second step is actually known as your back bonding. So when the back bonding is happening here, that time the LUMO will be what? LUMO will be your this pi star 2px and pi star 2py orbital. Okay, and once it donates the electrons to here, so what will happen? So see, so similarly it is donating electrons to here, and this bond will break and oxygen will be neutralized, because oxygen is already positively charged. When this bond breaks, oxygen is getting neutralized. So what we are getting? Metal double bond carbon. Okay, double bond O. Okay, so basically what we are getting? So here we are getting double bond. Okay, here we are getting double bond. Initially we have a single bond, but now we have double bond. Even if you see CO, initially you have triple bond. After back donation you are getting double bond. Okay.
Yes, sir.
So now the thing is, okay, write down one thing, that electron transfer, okay, electron transfer from metal to pi star of CO. Okay, metal to pi star of CO. So that time what will happen? That time bond order decreases, but that is for what? That is for actually CO. If you see CO, what is the bond order of CO initially when it is not bonding? 3, because if you have 3 bonds, so that means the bond order is 3. After back bonding, what is the bond order you are getting? 2, right? So that means the bond order is decreasing for your CO ligand. Okay, so I am doing one thing here. Write down that bond order of carbon oxygen bond is decreasing. Okay, bond order of carbon oxygen bond is decreasing. So if bond order is decreasing, what will decrease? Bond strength will also decrease, but bond length will increase. Okay, so bond order of carbon oxygen bond is decreasing, and similarly bond order of metal carbon bond is increasing. So if bond order is increasing, I can say the bond length, okay, bond length of your carbon oxygen bond, that will increase, and similarly here also the bond length of metal carbon bond, that will decrease. Okay, we have a relation like this: nu is equal to 1 by 2 pi what, root over of k by mu. Okay, so this k actually represent your bond strength. Okay, so if this k value is increasing, the stretching frequency value will also increase. Okay, we will see questions from this equation. So keep in mind, if your bond strength is bond order is increasing, bond strength will increase, and as well as your stretching frequency value will also increasing. Okay, mu is your stretching frequency. Clear? Any doubt?
Sir, if you mentioning metal and carbon bond length increases in left side, the right side will be decreases. Why? Below. Left side increases, on the right side decreases. Bond length, metal to carbon.
Bond length, yeah, that is increasing, na? Here if you see, what is the bond order of your CO? Initially you have 3. Okay, now after back bonding, I am talking about after back bonding. After back bonding, the bond order is becoming 2. So that means the bond order is decreasing. So that means the bond order is decreasing. And if you talk about this metal carbon bond, so initially you have only 1 bond. After back donation you are getting 2 bonds. So that means what? The bond order is increasing.
Yes, sir.
Clear now?
And
if bond order is decreasing or increasing, bond length is inversely proportional. So you just make it opposite. Okay?
Okay, sir. Okay, sir.
Okay, now next, write down that factors affecting back bonding. Okay, factors affecting pi back bonding. So here write down number 1, that charge on metal. Okay, charge on metal. So first of all write down, suppose write down one line that metal in low oxidation state. Okay, metal in low oxidation state, metal in low oxidation state. So that means what? Low oxidation state means like -1, okay, 0, 1, maximum 2. Okay, 2 is the limit, not more than that. Even +2 is not applicable, -2 is also here. Okay, so if metal is present in your low oxidation state, that time write down favors back bonding. So in another way you can say that metal should be electron rich. Okay, low oxidation state means what? The metal should be electron rich. Okay, metal should be electron rich, that is the thing. Clear?
Yes, sir.
So suppose, just a minute, you have three metals like this. Metal in -1, one is your neutral metal, and another will be like this, metal with +1. So yeah, now they are asking the donor ability.
-1. -1 neutral, then +1.
So same thing, -1 will be greater than your neutral, then it will be your +1. Another thing comes here, that when you have negative charge, so that means what? The size is increasing here. Okay, and if size is increasing, as well as the polarizability is also increasing here. Okay, and that means the donor ability is also increasing. And for cations, for cations what? The size is decreasing because the nuclear charge is high. So that means the polarizability that is also decreasing, and this donor ability that is also decreasing. Okay, so you can consider from the charge, you can just check your electron density, and you can check also size. Okay, fine. Now suppose you have this set of complexes. Suppose you have this manganese, then CO6 plus, this is one compound you have. Next you have this chromium CO6, and another one you will have vanadium CO6 minus. Okay, so this is your compound A, B, C. So you just arrange them in this order. First of all, arrange them order of back bonding. Okay, order of back bonding. Second, strength of metal carbon bond. Okay, and strength of CO bond. So that means carbon oxygen bond. So these are the three things you have to arrange. Okay, you have to arrange, do it. So first of all, you arrange them order of back bonding. Second thing, your strength of metal carbon bond, and third, your strength of CO bond. For these three complexes, do it.
the order of back bonding CBA, C greater than B, B greater than A. Then metal carbon, it is also CBA.
Okay.
Then strength of carbon and CO bond, it is also ABC.
Correct. So basically you have to check the charge here. So here vanadium is negatively charged, here chromium is your neutral, and here manganese is your positively charged. So that means it is your electron rich. So if your metal center is electron rich, so that means what? If I consider this bond, okay, so vanadium can easily back donate the electrons to the carbon center, and this bond will break. So that means what? The order of back bonding, definitely it will be your C greater than B greater than A, correct? Okay. And if metal is doing back bonding, so that means the metal carbon bond strength or bond order is also increasing, so that is also correct, C B A. And if metal carbon bond order is increasing, so that means the carbon oxygen bond will decrease, because you will form this. So metal carbon bond is becoming from 1 to 2, and carbon oxygen is becoming 3 to 2. So that means carbon oxygen is decreasing, so it will be A greater than B greater than C, correct? Good. Okay, now try for this one. Chromium CO whole 4 minus. Okay, then you have Fe CO whole 4 2 minus, then you have CO whole 4 minus, then you have Ni CO whole 4. Okay, so this is your A, B, C, D. So here also find out the back bonding order. Find it out, back bonding order.
So back bonding ABCD, sir.
Back bonding will be A, B, C, D, right?
A greater than B, B greater than C. And metal.
Correct. So this is your 4 minus, then here you have 2 minus. Okay, so this is your most electron rich metal center you have. So that means the back bonding will follow this order: A, B, C, D. Or you can write down like this also: chromium minus 4 will be greater than your iron, minus 2 which is also greater than your cobalt, minus 1 which is also greater than what? Nickel 0. Fine. Okay, now let's do this question. So suppose, write down first of all the question that which one of the following is most stable. Okay, which one of the following is most stable? So I am giving you some options: Fe CO whole 5. Okay, next you have Fe CO whole 4 2 minus, next you have Fe CO whole 6 2 plus. Okay, so these are the three compounds you have, A, B, C. They are asking which one of the following is most stable. Find it out. Done. So here also this thermodynamic stability, na? Write down this thermodynamic stability okay, this is actually proportional to what? This is actually proportional to your back bonding. Okay, so if your metal center is able to do more back bonding, so that means it is more thermodynamically stable. Why? Because the double bond is forming, you can see more easily it can form a double bond, right? So here if it is clear, then you can easily say which is your most stable. So compound B will be most stable because iron is present in -2 oxidation state. Okay, so yeah, B is most stable compound.
Then A.
Here they are asking the most one, so we are just mentioning this. Yeah, then it will be A, then it will be a C. Clear, this thing is clear. Now charge on metal and yeah, what are the things on metal center we are doing? Clear? Clear, this first point is clear, na? Charge on metal. Okay, now write down the number 2 point, that nature of ligand. Nature of ligand. Okay, so first of all write down only sigma donor. Suppose you have only sigma donor ligand. Okay, so how to identify which one is your sigma donor? So suppose you have ammonia. Okay, so you know ammonia has a lone pair, right? Ammonia has a lone pair, so ammonia will donate this lone pair to some metal center. Okay, so if ammonia donates only one lone pair, so that means it is your sigma donor ligand. Okay, so I am showing you, suppose ammonia is here and it is donating the electrons to the metal center, and metal center is already attached with your carbonyl compound. That is the thing. Okay, so if you are giving some sigma donor ligand, so that means this sigma donor ligand is donating some electrons to the metal center, and metal center is already attached with the carbonyl group. Clear? So how to identify sigma donor? So you can write down here that donates only one lone pair. Okay, if the ligand is donating only one lone pair, then we will consider it as your sigma donor ligand. Okay, so basically sigma donor is doing what? Sigma donor is doing what? It is increasing the electron density on your metal center. If it is donating electrons, so that means what? The electron density on this metal center, it is increasing, right? Now write down number 2. Suppose you have pi donor. Okay, so in pi donor basically you can consider water, okay, even chlorine also. So what is happening? See, oxygen has 2 lone pairs. Okay, so basically what will happen, if oxygen donates only one lone pair to the metal center, that time we will consider it as your what? Sigma donor. Okay, but if it is donating both the lone pairs, so suppose water is forming one like this, so what can happen? Water can also donate this electron density to the metal center. So by sigma donor, by if it is donating, write down more than one lone pair. Okay, so if it is donates more than one lone pair, then we will consider as your pi donor. Suppose this chlorine chlorine is also your pi donor because it has 3 lone pair. Okay, so basically here ammonia is donating only one lone pair, so the electron density is increasing, that is fine. But if you see here, water is donating both the lone pairs to the metal center, so that means the electron density further it is increasing here, right? Electron density is further increasing here. So if I want to know the back bonding order, okay, back bonding order between this sigma donor and pi donor ligand, can you tell me what will be the order? Okay, just a minute. हाँ बोलो, फिर क्लास ले रहा हूँ, आता हूँ ये लेके 5:30 6 बजे तक होता है ना फिलहाल। हम 10 मिनट पहले छोड़ दूँगा। ठीक है। ठीक है। नहीं, वो थोड़ा चावल किया था वो खा लिया। हाँ, थोड़ा चावल किया था वही खा लिया। हाँ ठीक है, रात में जल्दी खा लूँगा। सिरू के पास जाऊँगे ना। ठीक है। ठीक है। Yeah, sorry, yeah, tell me what is the order here of back bonding for sigma donor and pi donor ligands?
The pi donor is greater than sigma donor.
Pi donor is greater than sigma donor because here it is this ligand is donating 2 or 3 lone pairs, okay, and sigma donor is donating only one lone pair, okay. So basically this back bonding will be high for your pi donor ligands compared to your sigma donor ligands. Okay, compared to your sigma donor ligands. Clear? Any doubt?
No, sir, clear.
Clear. And another type of ligands we have, so we have sigma donor, we have pi donor, and another one we have, that is your pi acceptor. Okay, so number 3, write down pi acceptor. So acceptor terms actually comes by the name, you can predict. Acceptor means what? It is electron deficient, right? The ligand is electron deficient, so not actually electron deficient, so that means it has some vacant orbital to occupy the electrons, right? Because the ligands means you have already lone pairs, but still it has some vacant orbitals that it can accommodate some electrons there, okay. So suppose I am talking about your this ammonia and I am talking about pH3, okay, pH3 or PPH3, triphenyl phosphine, so both has lone pair. But if you see, ammonia is acting as a sigma donor ligand, okay, but PPH3 is not, PPH3 is also a sigma donor ligand, but as well as it is a pi acceptor ligand also. Why? 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 Because phosphorus has vacant d orbitals, okay, phosphorus has vacant d orbitals. Now see this energy order, you know, so suppose this is your energy, we have done this MOT, okay, molecular orbital theory. So if your electronegativity is increasing, the energy will decrease, right? That I told you. If electronegativity is increasing, what will happen? The energy will decrease, okay. Here we have done na for that thing, carbon oxygen we have done na here. This see, if the electronegativity of oxygen is high, so that means what? The energy is actually relatively low from your carbon orbital, okay. So now here also if you see, so suppose I have two things, I have nitrogen hydrogen bond and phosphorus hydrogen bond. So which one will lie down and which one will be lie up?
The phosphorus and hydrogen bond will lie up. Nitrogen ಮತ್ತೆ phosphorus below.
Nitrogen will lie down, right?
Okay.
Because the electronegativity of nitrogen is high. So this is your sigma orbital of your nitrogen hydrogen bond, and this will be your sigma orbital of your phosphorus hydrogen bond. Okay, now the sigma star will be here. This is the sigma star for your phosphorus hydrogen bond, and this will be the sigma star of your nitrogen hydrogen bond. So energy is increasing in this order. Now basically if you have sigma bond, so that means you have electrons here. These are not vacant orbitals. Okay, this nitrogen hydrogen and phosphorus hydrogen sigma bond, these are actually your vacant these are actually filled orbitals. You have electrons here, but sigma star are the vacant orbitals. So acceptor means they will accept the electrons here only. So which one is better, which one is your LUMO, this nitrogen hydrogen or phosphorus hydrogen?
Nitrogen.
No, LUMO means lowest unoccupied molecular orbital. So energetically which one is lowest, nitrogen hydrogen or phosphorus hydrogen? Phosphorus hydrogen. So that one will be your LUMO. If you have to check the HOMO, so that time it is your highest occupied molecular orbital. Okay, so that time it will be your phosphorus hydrogen. So phosphorus hydrogen is better HOMO, and your phosphorus hydrogen is your better LUMO. Clear?
Yes, sir.
Fine. So yeah, if they ask that why you are considering phosphorus hydrogen as your pi acceptor ligand, which orbital it will take electrons, don't say d orbital. Okay, most of the students say that phosphorus has vacant d orbital, so it will accept the electrons. So practically it is not like, theoretically you can say that, but research have proven nowadays that phosphorus is actually taking the electrons in this vacant sigma star orbitals. Okay, so that we have to answer from your MOT concept. Okay, so basically now tell me, so I hope this thing is clear. So what I can write down here. Okay, so suppose you have here PH3. Okay, PPH3 is there. PPH3 is donating the lone pair to the metal center, and this is the thing you have. Okay, so suppose this is one condition. Okay, this is your pi acceptor condition. So now tell me the back bonding order if I consider all the three things, sigma donor, pi donor and pi acceptor, I am considering all the three factors, then tell me the back bonding order. So what will be the back bonding order here? So see, here PPH3 is donating electrons to the metal center, that is fine. So it is acting also as a sigma donor, right? But what is happening, PPH3 has also this orbital, this sigma star orbital. Okay, so what will happen, metal will back donate the electrons to the PPH3, right? So here metal to sigma star orbital of this PPH3 is actually happening, this electron donation is happening. So that means what, ppH3 initially it is donating electron density to the metal center, then again metal is donating the electrons back to the sigma star orbital of your ppH3. So that means what? Electron density is increasing or decreasing? Decreasing, right? So the order will not change. Initially you will have pi donor ligands, okay, because that has maximum electron density. Then will be your sigma donor, okay. So sigma donor only you have one lone pair. In pi acceptor also you have one lone pair, but what is happening here? The metal is also donating the electrons to the vacant sigma star orbital. So electron density of metal is decreasing. So last one will be your pi acceptor, okay, pi acceptor. So in pi donor, electron density
Increase.
highest,
Highest.
or you can write down maximum, okay. In pi acceptor, the electron density is minimum, or you can mention lowest. Clear? Lowest on what? Highest on metal. Here also you just write down lowest on metal center. Clear? Any done? Any doubt here? So it is clear what is sigma donor ligand, what is pi donor ligand, and what is pi acceptor ligand, and what will be the back bonding order for them. It's clear now. Any doubt?
No, sir, clear. So in presence of NPH3?
In presence of NPH3
NPH.
does not exist actually. It can exist, but the thing is if you have this nitrogen, so 2p orbital is there, so this time the nitrogen electrons are actually yeah, nitrogen lone pair is actually involving in conjugation with the benzene ring, okay. So nitrogen, this lone pair is not available on nitrogen, okay, so it will not act as a good ligand, but phosphorus will act, okay.
Okay.
Here the reason is phosphorus has vacant d orbitals, okay. Nitrogen has no d orbitals. If you have to consider, if you have to compare between your nitrogen and phosphorus, that time you can give this explanation. But if they are asking, okay, metal is back donating the electrons to the phosphorus ppH3 ligand, in which orbital it is taking the electrons, that time if you mention that sir it is accepting the electrons in d orbital, it will be wrong, because recent research studies they have proven that by the MOT they have proven that ppH3 is taking the electrons in sigma star orbital, not on the d orbital, okay. So you have to mention sigma star, not d. Clear?
The carbonyl group, it will back the electron which orbital?
Carbonyl.
Yes, sir.
Carbonyl I have mentioned here, pi star 2px and pi star 2py. This is the LUMO, na?
Pi star.
Homo means what? Highest occupied molecular orbital. So that means the electron will be donated from this orbital. And LUMO means lowest unoccupied molecular orbital. So that means electrons will come to this orbital. Okay. So carbonyl will take electrons in this orbital. If metal is donating electrons, I mentioned here, this thing, see where I have mentioned here. If carbonyl is donating, that time it is your HOMO, sigma 2pz. If metal is donating back to the carbonyl, that time it is accepting in here, LUMO, pi star 2px and pi star 2py. Clear?
So pi star and sigma star, which one is more LUMO? Pi star and sigma star.
Which one is energetically low, that will be your more LUMO. LUMO, why you are considering this as your LUMO? Because it is energetically low, na? Energy is increasing from here to here, from this below to up, okay, down to up. So that means if you are suppose you have one HOMO here, basically how the electron transfer is happening, HOMO, and you will have here LUMO. So this is a HOMO LUMO energy gap, na? This energy gap should be minimum. Okay. This HOMO LUMO energy gap should be minimum. So suppose you have some HOMO and now you have some LUMO. So this is your pi star orbital, this is your sigma star orbital. So Tell me, where the electron will go first, here or here?
Faster.
Faster, because the distance is low. So same reason. Clear?
Yes, sir. Yes, sir.
The homolume energy gaps would be minimum. Fine. Now next we have, write down donor ability of phosphine. Donor ability of
Sir, in last case,
uh,
metal will donate the back electrons to phosphorus sigma star. The carbonyl it has a 5-star orbital.
It can donate in both ways. Okay.
Both. Okay.
It can donate in the both. Basically,
Okay.
what we are trying to show you that here the electron density is decreasing. Metal will donate to the carbonyl actually, but what is happening? Phosphorus is actually taking electrons from the metal center, so that means the electrons density is getting low here. Okay.
Okay, sir.
Okay, now see this donor ability of phosphine. So if I have this ligand, this is one phosphine ligand. Okay, now can you tell me which one will be the order? Donor ability of phosphine, what will be the order here?
Sir, DBAC.
DV?
AC.
DBAC. Okay. Why DBAC?
The phenyl group.
Okay, so basically see, here you have methyl. So what? You have plus I effect. Right. Here you have oxygen. So what you have plus M as well as you have minus I. If you have only fluorine, that time you will have minus I only. Right?
Yes, sir.
And if you have this kind of thing, so that will also show you plus M as well as what? Minus is also possible. Okay.
Yes.
Now the thing is, you cannot consider here by your organic chemistry. Okay, if you consider these things in organometallics, if you consider this basically this phosphine ligands, if you consider like this, so that will be wrong. Okay, so only in this phosphine we have to remember a order. That order we will only follow. Okay, you do not go with your organic concept here for the phosphine ligand. Okay, so you will keep in mind one order. So first of all, write down this is the donor ability basically, that alkyl greater than aryl greater than alkoxide, okay, greater than halide. So this is the donor ability order. So that means this phosphorus, what I have, CH3 CH3 CH3. Okay, it is greater than your phosphorus, phenyl. It is also greater than your OCH3. Yeah, so this order you have to remember specifically for this phosphine ligand. Okay, not for all ligands, but for phosphine ligands you have to remember this. Okay, alkyl greater than aryl greater than alkoxide greater than halide. Clear?
Yes, sir.
Okay, now I am giving one set of ligands. You just try to solve it. Do it. Donor, find out the donor ability between these ligands. Okay, if you have only sigma donor type of ligand, suppose you have cyclohexyl, ethyl, methyl, that time you can consider your plaza effect. Okay, but don't use the organic concept if you are comparing with different types of ligands. If you have only sigma donor, only pi donor, that time you can consider your organic concept. Okay,
The
but
CY means
CY means cyclohexyl.
cyclohexyl.
Cyclohexyl, this. Okay, so you have 3 cyclohexane ring with this phosphorus.
So please numbering ABCD.
No, you just tell me, na.
Then
ABC.
greater than B, greater than C.
Okay, A, B, C, D,
E, F.
E, F, G. Right. Yeah, now tell me.
B greater than C.
B greater than C.
Yes, sir.
A.
D greater than A.
No. The cyclohexyl is what? This is also sigma donor, na. This is not benzene. Cyclohexane means what? You have only this 6-membered ring only. Okay, then you have phosphorus. So this is your one thing. Ethyl means you know what is ethyl. CH3, CH2, phosphorus. And methyl means you know. So here only one carbon center is donating. Here 2 carbon centers are donating. So if I consider the plaza effect, okay, plaza effect, so definitely cyclohexyl will have higher plaza effect than your ethyl, than your methyl. Okay, so the donor ability will be this P Cy whole 3, which is greater than P Et whole 3, which is also greater than P Me whole 3, which is greater than what? Aryl, which one is aryl? So this phenyl one is your aryl. Phenyl means what? Phenyl means now you have benzene ring. Okay, phenyl means now you have benzene ring. So basically next will come your PPH3. Then what?
Then POH twice.
Which
Hello,
one?
OME twice.
OME. Alkoxide, both are alkoxide. OME and OPH both are alkoxide, but if you see the plaza effect of OME will be high. So POME whole 3 greater than what? POPH whole 3, and at last you will get PCl3. Clear?
Yes.
Fine. Now what about this? P Me3, here also write down that order of donor ability. So you have PME3, PET3, then you have pH Me2, then you have P CF3 whole 3. Okay, so this is your A, B, C, D. Tell me the order.
Sir, BACD. BACD.
BACD. So ethyl will come first, then methyl, because these are your sigma donor. Next, okay, so next will be your C, and last one will be your D. Correct. BACD. Fine. Now suppose you have this PME3, then you have phosphorus, phenyl, methyl, phosphorus, phenyl, methyl. Okay, and last you have PPH3. Okay, do this one. So this is your A, B, C, D. Yeah, try to do it. ABCD.
Sir, A greater than B, ABCD.
ABCD. So correct. So here it is your A greater than B, because here you have one phenyl ring. Next you have two phenyl rings. So B is greater than C, and then it will be D. Aryl rings is coming. Okay, fine. Another thing left. Suppose you have this phosphorus. They have given like this. Do it. So this is your compound A, this is your compound B, this is your compound C, and this is your compound D.
D, A, C, D, sir.
Why D will come here? Here you have fluorine. Fluorine means what? This is your minus I affecting group.
Yes, sir.
Fluorine will
B,
not
B.
show plus M, because fluorine is the most electronegative. Fluorine always show minus I.
Yes, sir. D greater than A.
D.
D, B.
B is greater than A. Fine. B is greater
Then
than
A
A.
greater than C greater than D.
Correct. So fluorine is showing your minus I effect. That is the only thing. And here methyl will show you plus I effect. Hydrogen will show you nothing. So B greater than A greater than C greater than D. Clear?
Clear.
Okay. So that is the first fine thing we have. Next, give a heading that metal olefin. Okay, so olefin means what? You have carbon carbon double bond. So this is your ethylene molecule, basically ethylene molecule. So if you have pi bond, if you have pi bond, so they are also pi acceptor ligands. Why? Because if you have pi bond, corresponding anti-bonding orbital will be your pi star. Okay, so if you have double bond or triple bond, they will accept the electrons from the metal centers in this pi star orbital. Which one is your vacant? Okay, so keep in mind this kind of double bond or triple bond compound, they are actually pi acceptor ligand. Okay, these are actually your pi acceptor ligand. So what will happen? This double bond will donate the electrons to the metal center, and metal will also back donate the electrons to where? To pi star of this carbon carbon double bond. Okay, clear?
Yes, sir.
How it is happening with your carbon carbon double bond? So what I can say, that carbon carbon, if metal back donates, if metal back donates the electrons to the carbon center, so that time what will happen? The metal olefin bond order will increase or decrease?
Bond order
Bond order, metal carbon bond order, if
increase.
metal back donates, so that time it will increase. Okay, and if metal carbon bond is increasing, olefin means what? Olefin means this double bond only. Okay, olefin means this double bond. So metal carbon bond order is increasing, so that means what? Carbon carbon bond order
Decrease.
decrease. Okay, carbon carbon bond order is decreasing. Okay, so I can also write down like this, that uh, on pi back bonding, on pi back bonding, okay, carbon carbon bond length, carbon carbon bond length is increasing. Okay, and this metal
Bond length decrease.
metal olefin distance or metal olefin bond length is decreasing. Clear?
Yes, sir. Clear.
Clear. So now tell me, I have one example. Suppose here I have this carbon carbon double bond, and here you have platinum, this side you have pph3. So this is the ligand you have. Platinum is donating electrons, platinum is the metal center, this is the ligand you have. So basically one bond is forming here. This is one compound you have, and here you have pph3, platinum, pph3. Then what I have? Carbon carbon double bond. So here I have cyanide, 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 cyanide. Okay, so now tell me what will happen? Back bonding order. Now tell me the back bonding order. This is your compound A, this is your compound B. Cyanide you can show like this, cyanide you can show like this also, carbon triple bond nitrogen. This is your cyanide. So tell me.
So B greater than A.
B greater than A, why?
The carbon carbon bond order, it will be decreases, so then it will shows the conjugation.
Conjugation with what?
C triple bond N.
So this cyanide is basically your minus I as well as minus M affecting group. Okay, so metal is doing back bonding. Okay, metal is back donating the electrons to the carbon center, so this bond will break, and ultimately this bond is breaking. So that means
Yes,
what?
sir.
Cyanide, this cyanide group, what? Helps to withdraw the electrons from the platinum center.
Center.
Okay, cyanide group helps to withdraw the electrons from the platinum center, and that's why this is actually your electron withdrawing group. So if you have electron withdrawing group, suppose you have minus I or minus M affecting group, they increases the back bonding. Okay, so electron withdrawing group increases what? Back bonding.
Back bonding.
So that's why B is greater than A. Clear?
That's all clear.
Clear. Yeah, so that is the thing. And here you can write down the data also. They have given the carbon carbon bond length. Carbon carbon bond length they have mentioned 1.45 angstrom. Okay, and for compound B they have given the carbon carbon bond length 1.49 angstrom. So why? So if your back bonding is high, so that means the platinum carbon bond order is increasing, carbon carbon bond order is decreasing. If carbon carbon bond order is decreasing, so that means the bond length is increasing. Clear?
Yes, sir.
This is your bond length. Okay, this angstrom they have given bond length. Okay, fine. Now suppose I have this rhodium, oxygen, okay, so this is your A bond, okay, and this is your B. So here they are actually comparing between this double bond and this double
B
bond.
greater than A.
So back bonding will be what? Yeah, back bonding will be here also what?
B
greater than A.
than A.
Okay, and you can write down the bond length order. Bond length will be what?
B greater than A.
Bond length. If back bonding is high, so that means what? Rhodium is donating electrons to here. Okay, so that means the rhodium carbon bond is becoming more. What? Rhodium carbon bond order is increasing. Carbon fluorine bond order, carbon carbon, this carbon carbon bond order is decreasing. Okay, this rhodium and this carbon, this bond order is increasing, this carbon carbon bond order is decreasing. So that means what? The bond length will
decrease.
So it will be B less than A.
So in last question, carbon carbon bond length will increases.
Inversely proportional to. Here we have done in the beginning of the class, where we have done. Yeah, this order. Bond order and bond strength, they are inversely proportional to your bond length. So if bond order is increasing, bond length will decrease. If bond order is decreasing, bond length will increase. That is the scenario. Okay.
Yes, sir.
So here if you see, here you have carbon fluorine bond. So back bonding is high in B, right?
Sir,
Because
in presence of B, but the bond order is less, sir.
What?
Sir, after the back bonding, in B, the carbon carbon double bond. Then after the back bonding, it will show a carbon single bond. So you are so B greater than A bond length.
Yeah. For carbon carbon, it will be B greater than A. If you consider the rhodium carbon bond, that time it will be your B less than A.
Okay.
Okay. For
Okay,
carbon carbon it will be B greater than A. But if you consider the rhodium and carbon bond, that time you will get this bond length.
Okay, sir.
Clear?
Yes, sir, clear.
Fine. So that's it. Okay. Later we have something, so that we will do in the next class. We have what we have this: arrange the following increasing of stretching frequency, that we will do in the next class. Fine. Any
Okay.
doubt?
No, sir.
No, right. Okay, so study up to that. Okay, and I will take one assignment from organic chemistry. I am planning. Okay, in the next week I will take. So yeah, let's see when it is actually coming. Okay, then I will mention, I will post in the group, so according to that I will take. Okay.
Okay, sir.
Okay, bye. Thank you.
Okay, sir. Thank you.
Thank you so much. Bye.